This is Chapter 4, Section 4, Optimization number 15. This is more like the type of question you would get on an AP test. So you have a box with a square base and the volume of 100 cubic meters. So let's draw a picture. So the base is square. We don't know how long it is, but since it's a square base, we know those are the same length. We don't know how long it is that way. We'll call that h. Okay? And what do they tell us? The volume is 100 cubic meters. And it's important to know what they're trying to find. Uh-oh, my little thing has disappeared. Oh, there it is. They want the minimum surface area. That's the key word. You're trying to minimize the surface area. So what is the surface area, which I'll call A? It's the area of all the sides. We can do that. What's the area of this side? It's x squared because it's this times this, right? And what's the area of this side here? It's this times this, so that would be xh. And what's the area of the top piece? It's x times h, so that's going to be xh. So what is the total surface area? I have two of these, one on each end, so it's going to be 2x squared. And I'm going to have two of these, top and bottom, so that's 2xh. And I'm going to have two of these, left side and right side, so that's going to be 2xh. So my surface area is 2x squared plus 4xh. I'm trying to minimize the surface area. I want this to be a minimum. It occurs at critical points and endpoints. So how do I find critical points? I need to take the derivative, but here's my problem. I have two variables, x and h. So I need another equation that I can eliminate one of those with. And so here's the magic. Here's the only other piece of information we haven't used. The volume is 100 cubic meters. But what is the volume? Length times width times height. So x times h is 100. X squared h is 100. I'm going to solve for h. I could solve for x or h, but I don't want to square root. So I'm going to solve for h. It's 100 over x squared. So what does that do for me? That makes life easier because I can put this in for the h. So my surface area is 2x squared plus 4x times 100 over x squared. And this simplifies to this, 400 over x, because one of these cancels one of those. And to make the derivative much easier, I'm going to move the x on top and get x to negative 1 power. Okay? So I want the derivative because I want to find the critical points, because that's where max and mins can occur, critical points or endpoints. The derivative would be 4x minus 400 x to negative 2, which is 4x minus 400 over x squared. I still have to find the critical points. Where is this 0 and where is this undefined? So I'm going to get a common denominator, x squared, by multiplying top and bottom by x squared. And that gets me 4x cubed minus 400 over x squared. And now I can find where the derivative equals 0. That's where the numerator equals 0. Add 400 to both sides. Divide both sides by 4. And cube root both sides. And then where else could it happen? If the denominator is 0. A prime is undefined if the denominator is 0. Well, that's at x equals 0. So those are my values of critical points, but I claim this is not a critical point. That's actually an endpoint. Why is that an endpoint? Well, your box, the minimum value for x is 0. I know it makes no sense for these to be 0. You wouldn't really have a box, but that's the smallest theoretically x could be. Now, how big can x go? Well, here's where it gets weird. The smaller these get, the longer h gets. And if these approach 0, h goes to infinity. So actually, we don't have a right endpoint. It's infinity. Okay? Or I actually went the wrong way. If h goes to 0, x is going to go to infinity because it's going to keep getting bigger because the volume has to be 100. So if h approaches 0, these have to get super ginormous. So that's my domain of x, which I don't like because it doesn't have an endpoint. But here's the deal. Remember that theorem that says if you have a continuous function with one relative extrema, it is an absolute extrema? That's what we're going to take advantage here. Looks like we have one relative extrema. So let's do this. It appears we have one relative extrema, the cube root of 100, and we're going to see if it's a relative max or min. So what is the cube root of 100? I don't even know. I'm going to do that in my calculator. 100 to the 1/3 power. That's about 4.6. That's about 4.6. So I'll pick a number smaller than that, 4, and a number bigger than that, 10. We put that into our derivative right here. If we put a 4 there and there, what is that? That's going to be 4 to the 4th. 256 minus 400. The top's going to be negative, and the bottom's going to be positive. So if we do that, this is going to be negative. We put a 10 here. It's 1,000, 4,000 minus 400. That's positive. That's positive. So here's what's happening. This is a relative min because the derivative changed from negative to positive. So I would have to write out there's a relative min at x equals cube root of 100 because a prime changes from negative to positive, right? And then I would say since this is continuous and that is the only relative extrema, therefore there's an absolute minimum at that point. That's how you would do that.